Ben. I'm a tech lead at Snowplow. So it's a startup providing a pipeline, an analytics pipeline. And yeah, that's pretty much it. And today I'm going to talk about Apache Spark. So in and out. So what we're going to do is try to zoom in into the batch APIs at the code level, and then zoom back out at more of an ops kind of tech ops level to see how a Spark job can be run on EMR, on AWS EMR, and how it can be tuned to get the most out of your money on AWS. So quickly, what we're gonna go through. So first, we're gonna try to have a look at the different batch APIs, how they differ, and which one is the most appropriate in which cases. Then we're gonna go through a couple of examples that are part of the Snowplow pipeline. So all the code we use in Snowplow is open source. So what I'm going to show is an extract of those Spark jobs, but there will be links inside the presentation, so you can go check them out afterwards on GitHub. Then we're gonna try to see where the APIs fall short, and what we can do to improve on them. And then we're gonna zoom back out and try to see how we can run a Spark job and tune the configuration on AWS EMR. So first up, so Apache Spark. If you guys don't know anything about it, it's a big data framework, an open source big data framework, and it's split into different models. So you have the Apache Spark core, on which all the other models are built upon, and different layers of APIs depending on your needs. So today we're gonna talk about Spark SQL and the core Apache Spark API, but there are others models depending on your use case. So for example, if you do streaming, you might be interested in the Spark streaming module. If you do some machine learning, there is also a module dedicated to it called MLlib. And then if you do graph processing, there is a module called GraphX. And so Apache Spark is a framework and has different APIs. And so quickly, how does it look like? So for batch processing, there are 4 different APIs, and I'm just gonna showcase them quickly by doing a simple word count. So I'm gonna try to go from the top dataset, which has basically 2 columns, column ID and a column word, and we're gonna try to obtain the second dataset, which computed the counts of every word. So since Scala appears twice, it has the count too. So first up is the historical API. So when Spark was first released, it contained the RDD API. So what's an RDD quickly? It stands for Resilient Distributed Dataset. So basically, it's a collection of JVM object which is distributed across different machines, and it's strongly typed. So the API that was built around the RDD is kind of similar to what you might be used to programming in Scala. So it looks pretty much like the Scala collection API. So you can do maps, filters, all that kind of stuff. So right for this word count, we're just computing the count by mapping over our over each line and assigning it the count 1, and then using the reduce by key operation, which just sums every value grouped by key. And then you have another API which came long after the RDD API, where you can do SQL. So just like you would do for any single node database. And so you write your SQL as you would do, and get your results out. In parallel to that, there is also the data frame API. So if you are familiar with the data frames in R, that's pretty much the same thing. So it's just a table with named columns with which you can interact using an API that kind of looks like the Scala collection API and kind of looks like SQL. So it's a mix of both, but it's untyped. So as you can see, you refer to column as simple strings. And then finally you have the dataset API. So here it's the best of both worlds, kind of, because you have access to the type of each record in your dataset, and so you can access columns by through a lambda and not by a simple string. So now that we've quickly looked at what those APIs look like, let's compare them and go a bit deeper. So basically, this table sums up the differences between those APIs across a few different criteria. So what we're gonna try to compare is like what the code looks like as we've just seen, how the datasets are stored in memory, whether or not the API allows for query optimization. So basically, as you would find in a single node database, when you write SQL, for example, your query is translated into a query plan before being executed, and so Spark does this for a few APIs. Whether or not it performs code generation. So one nice performance improvement that came to Spark is that Spark is able to generate JVM bytecode directly from your operations. So that saves a bit of time since you don't since you bypass the JVM for generating bytecode. Also, we're going to look at whether or not syntax errors are caught at compile time or runtime, and whether or not analysis errors are caught at compile time or runtime. So for RDDs, so that was the first API that Spark was released with. So as we've just seen, the API looks more or less like Scala collections, and in memory it relies entirely on the JVM to store data. So you have JVM objects. So yeah, each record is handled by the JVM, and so you have some overhead, as you might know, when you store objects in the JVM. Since there is no query per se, there is no optimization performed for RDDs. So what you code is what will happen directly. There is no translation or optimization performed by Spark. There is no code generation either. So your operation will have to be translated into bytecode before being shipped off to your nodes. And since it's RDDs are strongly typed, you catch syntax errors at compile time. You cannot reference a non-existing property of an element in your datasets if it doesn't exist. And since there is no query optimization and no analysis of what you're trying to do, there are no analysis errors that can be possible. So next up, so for the SQL API, so it just looks like SQL because the SQL standard has been implemented by Apache Spark. So what you could do on your single node database, you will be able to do in a distributed setting in Apache Spark. Next up, the storage, the data storage is performed by Spark. So what they do is that they have their own way of laying out objects in memory, and that happens off the JVM heap. So everything is carefully laid out in memory, and what they try to do is try to limit as much as possible the overhead of accessing an object, storing an object. And so what ends up happening is that you save quite a bit of RAM because you don't have to deal with this overhead. And so for SQL as well, the query optimization is performed since your SQL statement will be translated into a query plan that will be that will try to find any optimization that's possible. And they also rely on code generation. So if you, for example, if you try to do let's say you want to filter out a part of your data, bytecode will be generated on the fly, and so you won't have to. You will bypass the JVM for bytecode generation. But the problem with the SQL API is that both syntax and analysis errors are caught on runtime because when you compile your SQL statement is just a string, so the compiler doesn't know anything about what you're trying to do, and so you might misspell something, you might reference a column that does not exist, and that will only be caught at runtime. And so for data frame, the API is a bit different, as we've seen. It's a bit of a mix between Scala and SQL, as you can do selects, but you can also it's a mix of both. For in-memory query optimization and code generation, it's the same as SQL, so they all rely under the hood on the same API. So yeah, it's all the same for those. But syntax errors are caught at compile time, so you cannot. If you're trying to do a group by, there is a method called group by, so you cannot bypass those errors at compile time. But however, since you're referencing column names as simple strings, analysis errors can and will happen at runtime. So it's the main drawback. So finally, the dataset. So it's the best of both worlds. you have the expressiveness and type safety of RDDs, but you also have all the optimization that have been performed for the data frame API. But as we will see a bit later in the presentation, it's not always enough. So next up, we're gonna try to look at a couple of real-world examples. So what I'm gonna detail next is two Spark jobs that we run for batch pipeline at Snowplow. So first up is the enrich job. So as we are as we have built an analytics pipeline, what we try to do is enrich the data that comes in with some interesting data. So for example, let's say that your event comes in with an IP, and a possible enrichment would be to perform GeoIP lookups. So based on your IP, try to output where this IP comes from. So that's one example of an enrichment, but there are many others. So basically what the enrich job does, if we simplify things as much as possible, is that we will have to rely on the RDD API to read our data, because we support a couple of different input formats, and so there is Swift encoded LZO compressed data on one hand, and simple gzipped data on the other. So since we have to support both those input formats, we have to rely on the RDD API. And since our job is fairly simple, we have a magic function that's just enrich our events for us. We just do a map over all our events. We don't necessarily have to rely on the dataset API, because we know that the query optimization wouldn't lead to any improvement, since we do a basic map. And so once this enrichment is performed, what we get out is multiple enriched events that have been validated. So which means that we either get events that have been properly enriched, or events that have failed enrichment. So to try to not lose any data, we will write the bad events on one hand and the good events on the other hand. And so what we end up with is projecting the bad events on one hand and projecting the bad events on the other hand, and at the end we rely on both the data frame and dataset API to write out our results, because those the APIs to write out data for data frames and dataset is much nicer and lets you do a lot more than the RDD API. That's why we convert our initial RDDs into data frames and datasets. So that's basically what the enrich job does. And next up is the shred job. So it's a bit more complicated. So the goal of the shred job is to prepare the data for storage. So for example, in Redshift. So what we're going to try to do is inspect our events to validate the the different JSON they contain. So let's say you want to send let's say you have a mobile application and you send an event. You send events to monitor like the health of your application. What you can do is attach to this event a context that will add additional additional context to your event. So for example, you might want to set an event that your app has been launched, but you might want to attach the context that it has been launched from an Android device, which was a Samsung S8, for example, and so this added context is contained into a JSON inside the event. And so what the shredding process will do is try to separate those events from the original enriched event, validate that the JSON is correct, and write them out to another location so that they can be ready to be imported into a database and a specific table. So in the end, you will have a table in your database for each one of your contexts. So if we go through the code, so we read back what the enriched job has outputted, and we are gonna try to shred them. So basically, try to separate the JSONs inside the event. Once that is done, we project, just as we've done for the enriched job, the bad events, so those that have failed shredding from those that have succeeded shredding, and then we can address the other responsibility for the shred job, which is to deduplicate events. So let's go back to our application that we want to monitor. So let's say you're trying to set events, but unfortunately, the device on which your application is running is encountering connection issues. So it's trying to send events, but they come back as having failed sending. So what that means for the client is that they will keep on retrying to send your event until it appears as succeeded. So on the back end, what you might end up with is a lot of duplicated events. And so what we try to do is deduplicate those events. So what that means is that if they have the same event ID and event fingerprint, which is basically a hash of the whole event, that means those events are duplicates. So we will just only keep one. And so that's deduplication in a batch. What we additionally do is try to deduplicate those events across different batches. So if you run your analytics pipeline, let's say every hour, you might end up with duplicates into two different batches. And what we do is deduplicate across those batches. So let's say that so that's an added functionality that can be configured. Like, let's say you want to deduplicate across the batch for a whole day, you will be able to do so. And so after all this deduplication has taken place, we are ready to write out our bad data. So this is the entirety of the bad data is the data that has failed shredding and which also has failed deduplication. So that's what you see in the bad plus dedup failed. So we add those datasets and we write them out to the bad output path. And for the event which have succeeded the duplication, we write the original events back to some place. And finally, all the shredded types that we have discovered during shredding are being written to yet another place. And once this job has taken place, another application will look through those two paths and load the data that they contain into an analytics database. So, for example, Redshift. And so so I've tried to simplify as much as possible those examples, but if you're curious, you can check out the code in its entirety since it's on GitHub. So you can check it out afterwards. Okay, so that's all good and well. So, but there are a few issues with even the dataset API. So I've not showcased them in the different example we've seen so far, but it's important to keep them in mind, since because the dataset API inherits from the data frame API, you still can do some operations that are not strongly typed. So if we go back to the word count example, with the dataset, you're still able to select and reference columns that with simple strings. So, for example, here I'm selecting a column which is named not word, and unfortunately, this issue will only be caught at runtime, so not at compile time. And so there is a nice library by the type level organization, if you're familiar, which is called Frameless. And what this library is trying to do is to bring even more type safety to the dataset API. So it's easy to create a type dataset. You just have to pass your dataset as an argument, and what you're able to do next is every operation you can think of will be checked at compile time. So you cannot reference columns that are not existing or anything like that. So for example, here we're trying to select the not word column, and since it doesn't exist in the dataset, it won't compile. So you save quite a lot of time, since you won't have to run your Spark job to find out that you've made a mistake. And another nice benefit is that they also overload the as method. So when you perform operations on your dataset, the schema of your data will be transformed, and you will lose at some point. Yeah, you will almost always lose your initial schema. So before we had ID word, and after our word count, we end up with a word as well as a count. And so if we want to go back to type safety, Spark defines an operator called as, and where you can pass your case class to get back to type safe land. But unfortunately, this operator does not check that your schema conforms to or fits your case class at compile time. It will only check it at runtime. And so what Frameless does is that they define their own as operator, which checks the fitness of your data against your case class at compile time. So that's two very nice benefits from the Frameless library, but there are many others. So I invite you to check it out. And next up is a small library that I wrote because I was becoming frustrated with with the way data is read in Spark. So what you usually end up is trying to read some data, like let's say JSON data from somewhere in HDFS or even the local file system. And what you want is directly to be able to interact with the data in a type safe manner. So you directly use the as operator to get a data set which has the my case class type. But unfortunately, the problem is that the API the API will try to infer the schema of your data. So what Spark does do in the end is that it will go through every record in your data and try to come up with a schema that is the union of all possible schema. So for example, if you have 2 million records, and it will go through every one of them and come up with a schema for each of them, and then combine all of those schemas into one. And so the problem is that it's very time consuming to do it, and it's almost always not useful, because you will try to get back to type safety as soon as possible, and so the schema of your case class. You've defined it as a case class, and so to bypass this, the inference of all of the different schemas, you can specify your own schema. But the problem is that it's very annoying to do, because it's very boilerplate heavy, because you have to basically redefine your case class as a schema and specify the type every time. And if you want to modify your case class, so let's say your data has changed and for example, you've added a field, you now have two sources of truth, your case class as well as your schema. So I wrote a small utility to directly derive your schema from your case class without having to manually write your schema. So basically, you just give it the type of your case class, and it will produce a schema that Spark can understand, and so that it won't go through all of your data to try to infer the schema. And so in the different benchmarks I did, it approximately saves around 10% of 10% of time trying to read data. There are also a few other features, but I won't go into them too much. So now that we've dived deep into the APIs and what are they good for and what are their shortcomings, we can try to zoom out and see how a Spark job can be run on AWS. So what we use at Snowplow is EMR. So basically, it stands for Elastic MapReduce, and it provides a managed Hadoop and Spark and other big data technologies clusters. And what we found out using EMR is that Amazon is very conservative into what they give you. So I'm going to take an example. So let's say I have a 60 gig of RAMs machine with I don't know, 8 cores. What AWS will make available to your Spark job is only 2/3 of your machine. So as I said, if I have 60 gigs of RAM, only 40 will be made available to my Spark job. So it's something to keep in mind, because if you want to utilize your resources as much as possible and try to get as much value for your money, you will have to try to manually tune your EMR cluster. And so that's what I'm showcasing here. So on the left, you can see the AWS CLI for a usual Spark job, and on the right is a sample of the configuration that we use at Snowplow to get the most of our EMR instances. So in this example, I have a NERF 4XL EC2 instance, and so this instance has 122 gigs of RAM for 16 cores. And so without any configurations, if I let AWS EMR run everything by itself, only 90 gigs of RAM will be made available to Spark. So if we want to try and maximize the resource utilization of our cluster, there is a small amount of tuning to do. So in this case, I just leave 5 gigs of RAM to the OS and use the 117 that are left for Spark. And after that, so on each of my EC2 instance, I will make what Spark calls executors available. So that's basically what a unit that is capable of doing work inside Spark. So you have on one hand you have a driver which will be responsible for giving tasks to executors, which will be responsible for executing them at if we simplify things as much as possible. And so each of those those like driver and executors will have to be tuned. So you give a fixed amount of memory to each executor and a fixed amount of cores. And so to maximize resource utilization, there is a Spark configuration cheat sheet. So that I'm going to show you. So there is the link is will be on in the presentation. And what this this cheat sheet provides is a way to configure your cluster for you without you having to perform too many calculations. So in our case, we have one R44XL. So that's a machine which has 122 gigs of RAM for 16 cores. So all the calculations, all the configuration calculations are performed by the spreadsheet. So it's very convenient. And what it provides is a set of settings for which you can choose from. So here I just inputted that I have only one node. This node has I shouldn't say 132 because I have reserved 5 gigs for iOS. So I have 170 gigs of RAM available to my Spark process. I'm also going to remove one course for iOS. And so this is what one instance of R44XL gives me basically. And so I'm going to be able to choose a number of executors per node while trying to minimize the amount of unused memory per node and unused core per node. So in this case, it gives me 7. So if I just input this into this field, it will give me all the configuration necessary for my Spark job without me having to manually compute those values. So it's pretty useful, and there is a lot of customization that can be done depending on your workload. For example, if you do a lot of group buys of operation that will need shuffles across different nodes, you can customize the spreadsheet to take this into account and make your job perform as well as possible. So yep, that's it for me. Yep, if you guys have any questions, I will be happy to answer any of them. I think you're muted. I can't hear you.
Thanks. Just want to say thanks for your presentation.
Yeah, no problem.
Now let's see. Let me maybe ask. Let's see. Maybe questions on the chat. Okay. Uh, if someone has a question that wants to ask live, the question was, uh, how much volume do you process in terabytes of data usually per hour or per
I'm
day?
sorry. Yeah, I
Uh,
couldn't hear you.
Let me repeat. Don't worry. Actually, we have a lot of questions. uh, Let me first tell you. How much volume of data do you process usually? Like terabytes,
Yeah.
maybe per
So
hour, per day?
yeah. So what's interesting with Snowplow is that we run the pipeline for our customers. So there is no sharing between customers. So we have very small customers that run very small pipelines, like let's say I don't know 1 gigs of data per hour, and we have much bigger customers which which clock at a few hundreds of gigabytes per hour. So we have very different pipeline size. So that's why it's very important to manually tune them as much as possible. So we don't incur too much AWS charges for our customers.
Okay. Next question. How to integrate Spark with web services? There are some best practices.
If I understand correctly that it's how to integrate Spark with web services.
Yes, that was correct.
Yeah. Okay. So
There are some best
it depends
practices.
on So it depends on what you want to do, because um, so for example, in my previous job, what we had was a long-running streaming job that had to interact with a a web services to dynamically collect different queries to run on the stream. So what we had is for on each executor we had a request made every X seconds to the web service, and and this the result of this request was cached, so that like every X seconds the cache was invalidated and a new request was made. So I don't know if this answers the question. Maybe.
Okay, yeah, one use case. Next question. What kind of cluster manager do you use?
So
Mesos,
with
Yarn, or others?
Yeah. So with AWS EMR, you don't have a choice. It's Yarn that is imposed by AWS. So we use Yarn. And but yeah. So in my previous job, we we ran different. We tried different cluster managers. So basically Mesos and Yarn. And the feedback was that Yarn is easier to to maintain for ops people than Mesos. But maybe this situation has changed. I don't know.
Okay. Next question. How to implement processing algorithms that have sequential steps which cannot be parallelized?
I couldn't hear you. I'm sorry.
Okay, let me repeat. So, how do you implement processing pipelines or algorithms that are sequential in nature, so they cannot be parallelized?
So
on Spark?
yeah, I can say that I've had to do it myself, but I know that inside Spark itself there are a few of the machine learning algorithms face the same issue, and what they do is basically to try to condense those operations that cannot be parallelized as much as possible, and basically do a big map over the records. But yeah, maybe there are other approaches that are better. But yeah, I invite the people that ask this question to look at the implementation of the machine learning algorithm, because they face the same issue.
Okay. Are you using Java API or PySpark?
Yeah. So Snowplow is divided into different teams, and so I'm part of the data engineering team, and the data engineering team only use the Scala API, as I've showcased in the presentation. But we have analysts that are more familiar with Python, so they use PySpark, and from what I hear, the feedback is pretty good. So yeah, basically it depends on what you're most familiar with. I know that in the past the Python API wasn't as good as the JVM API, but I think lately they've been improving on this front.
Okay. Do you know any real use cases for graphics?
I think yeah. So a few I think last year one of my colleague tried to represent data in our data or analytics data in a graph database, and so he used graphics to analyze the data. So kind of so yeah, basically what you need is data that can be represented as a graph. So for example, social media data, or yeah, any kind of data that is representable as a graph, and then you can rely on graphics. But yeah, I haven't used it myself.
Okay. And the last question was maybe you can give some examples or information in stateful computations or streaming, Spark streaming, I guess.
Yeah, sorry, I couldn't hear you again. I'm sorry, the connection is
No
really bad.
problem. Yeah. Have you ever used or maybe know some examples of stateful computations on Spark or Spark streaming?
In batch, I think you can try and have a look at the machine learning algorithm, because some of them are stateful. Regarding streaming, nothing comes to mind. But yeah, I'm sure some people have done it before.
Okay. It seems like I just heard in Spark we use like micro batches rather than actual streams. I haven't used myself. Anyway, so thank you, Ben, for your time and your shared experience. The topic was there. There are some comments online. So anyway, thank you for your time and
Thanks.
nice
Thank
to
you.
you.
Yeah, thanks.
Cheers.
Bye bye.